Hello, my name is Nico Jansen and I now present the master thesis from MontiCore to Ecore, bridging the gap between grammars and metamodels. First, I start with a brief motivation. So, in general, there are two common approaches of developing new modeling languages. The first approach is based on grammars, which allow the simultaneous definition of concrete and abstract syntax in a single effort, and also facilitate textual modeling. The second approach is based on metamodels, and here the language developer directly modifies the abstract syntax representation of the underlying metamodel. The benefit of using standardized metamodels is that there is a wide range of tooling possibilities for the corresponding DSL. And that's exactly the problem for many grammar-based language workbenches, since in general they do not feature that many tooling possibilities, which is, for example, available for EMF. So our idea was creating corresponding metamodels from grammars to enable further tooling such as visualization via Sirius or differentiation with EMF compare and interpretation with Gmod Studio. Therefore, the goal is translating MontiCore grammars into corresponding Ecore metamodels. As additional motivation, we have this little visualization tool for MontiArc, which we developed with Sirius. So here we see the different elements of a component and connector architecture with the different components, subcomponents, ports, and connectors. And this should just give a little outlook what's actually possible with our approach. Our concept is based on the generation of metamodels from grammar-based DSLs. For our realization in MontiCore, we use the MontiCore feature of generating EMF-conform abstract syntax classes. These classes are compatible with applications which are based on EMF. However, in general, this is not sufficient, since many tools expect the metamodel as input as well. Therefore, we aim at serializing these EMF-compatible abstract syntax classes into a corresponding Ecore metamodel. Important is the correct translation of MontiCore-specific features, for example grammar intricacies such as nonterminal references. MontiCore also generates a parser to process the textual models. Additionally, this parser performs a syntactical validation of these models. Since there is no parser available on the EMF side, we need to integrate this validation functionality into the Ecore metamodel as well. Therefore, we extend the static semantics of the corresponding metamodel. Here, we use for example OCL constraints, since EMF supports OCL to enrich the metamodel with further information. We also aim at integrating the automatic model verification of MontiCore's parser in EMF. Here, we provide Java methods to validate the corresponding model instances. This is important to ensure model validity in EMF as well. Otherwise, well-formedness cannot be guaranteed once a model is modified by a developer or tool. Challenges were exactly the translation of these MontiCore-specific features, such as non-terminal references, but also the correct integration of cardinalities. The cardinalities in the abstract syntax only represent rough boundary values for the actual cardinality restrictions of the underlying grammar. The same holds for the translation of exclusive disjunctions. In the following, we explain these challenges with this exemplary MontiCore grammar for describing a tennis tournament. A tournament has a name and can consist of multiple matches with 2 players each, so we always require an even number of player instances. A tournament can also have several referees. Finally, a tournament might or might not have a winner. We express this with the optional winner non-terminal reference. A player has a name. A referee has also a name and additionally a qualification, which is an enumeration with the values good or bad. To indicate the problems for the grammar, we investigate the corresponding abstract syntax representation. The class tournament contains the string attributes name and winner, as well as the 2 compositions players and referees. Concerning non-terminal references, the class only contains the original string variable winner, but not the referent itself. So we lose the information that the corresponding value actually points at an existing player instance with matching name attribute. Another problem occurs regarding the cardinality values of the composition's players and referees. In the abstract syntax representation, both are expressed as lists. Here we for example lose the information that the tournament requires an even number of players. Finally, the class diagram only features placeholders for the alternatives of the exclusive disjunction, but not the disjunction itself. The disjunction describes with respect to the plus cardinality of the surrounding block that at least one of these alternatives must be selected. The abstract syntax also accepts a tournament with no players and referees at all. However, this deviates from the models described by the grammar. This describes the challenges of our approach. In the following, we investigate the corresponding solutions. In the case of non-terminal references, we resolve the implicit reference in MontiCore and express it as explicit association in the Metamodel. In this case, we create for the non-terminal reference winners toward an existing player instance the association winner-player between the corresponding classes. The original string attribute winner is set to derived, since its information is now provided by the established association. Additionally, the string attribute name of class player is marked as ID in the Ecore Metamodel. This ensures that its value is unique among all instances of the according class, which is a requirement of the symbol definition of the non-terminal player in the MontiCore grammar. Finally, we use OCL to define the derivation for the derived attribute winner. In line 7, we set its value to winnerPlayer.name, which is the expected value concerning the underlying reference. With this approach, we properly express non-terminal references in Ecore metamodels. Regarding cardinalities and exclusive disjunctions, we had the problem that these values are not correctly represented in the abstract syntax. Instead, the parser, which MontiCore generates, evaluates the local cardinality restrictions. To integrate this validation into the EMF metamodel, we generate an explicit validate method for each of the corresponding abstract syntax classes. In this example, we generate the Boolean validate method for the class tournament. The validate method operates on the numbers of instantiations of the corresponding attributes for the class. For the given grammar excerpt, it requires the parameters player size and referee size. The validate method evaluates the validity of the model concerning the local cardinality restrictions of the grammar and the actual number of instantiations for the corresponding attributes. Finally, we use an OCL constraint, validate model, to invoke the validate method and pass the corresponding parameters player size and referee size. This explains the conceptual realization of integrating MontiCore's parser validation into EMF metamodels. Now we need to capture the grammar intricacies for the validate method in the first place. For this reason, we introduce the concept of production graphs. We use these graphs to store production rules in a graph-like notation and capture local cardinality restrictions on which cardinalities and exclusive disjunctions depend. In our approach, we translate the particular language elements, in this case non-terminal instances, which are represented as attributes in the abstract syntax, and blocks. Non-terminal instances are translated into attribute nodes, which are represented as rectangles with the corresponding usage name of the attribute. Blocks, which influence the local cardinality restrictions as structural features as well, we translate into corresponding block nodes, which are represented as circles with cardinality values. Finally, we normalize these graphs to provide them for the derivation of linear equation systems. The idea is that these linear equation systems contain the corresponding local cardinality restrictions of a grammar. We integrate the linear equation systems in the validate method which tries to solve these systems with respect to the given attribute instantiations. If the validate method finds a solution for one of the given linear equation systems, then the corresponding model is valid. Otherwise, it is rejected. As shown on the last slide, we use an OCL invariant for invoking the corresponding method and providing the parameters required to solve the linear equation systems. In the following, we explain how to create and normalize production graphs. We create a production graph for each production rule in the grammar. In this example, we use the first rule of our tennis tournament grammar. The first occurrence of a non-terminal is name. Therefore, we create a corresponding attribute node name. In the next step, we translate the corresponding block. Here, we create a block starting and a block ending node, which contains the corresponding cardinality of the block in the grammar. The block itself contains the language elements of the production rule. In this case, there are two alternatives. The first alternative contains two instantiations of the non-terminal player, and the second alternative consists of a single referee instance. In the production graph, we create the corresponding attribute nodes. Here, we translate concatenations in a grammar as successor relations in a graph and alternatives as sibling relations. Finally, we also translate the optional non-terminal reference winner. Here, we extract the cardinality value of the attribute directly to a surrounding block node. Now the graph is completely created and ready for normalization. A normalized graph contains only attribute nodes and block nodes with a star cardinality. Therefore, the normalization steps include eliminating block nodes of default, plus, and optional cardinality. As first normalization step, we eliminate blocks of optional cardinality. Therefore, we remove the cardinality value of the block and exchange it with a default cardinality. In addition to that, we add a branch with an empty attribute node. This newly added empty branch represents the actual optionality without using the cardinality value itself. In the next step, we remove plus cardinalities from the graph. Here, we exchange the plus cardinality by a star cardinality block and extract the first iteration into a default cardinality block. This way, we represent the original plus cardinality by the combination of a default and star cardinality. Finally, we remove block nodes of default cardinality in the graph. Therefore, we simply eliminate the corresponding start and ending nodes of the block. Additionally, we merge the different branches, which represent the alternatives in the production, at the root level of the corresponding graph. This is important for the following derivation of the linear equation systems. In this example, we obtain 4 branches for the combinations of the alternatives represented in the 2 default blocks. The branches merge again at the only remaining star block node. Finally, the graph is normalized and contains only attribute nodes and block nodes with star cardinality. After the normalization of the graphs, we can now derive corresponding linear equation systems which represent the grammar intricacies for the language. For each of the root branches, we create exactly one equation system. For this reason, it was important to merge the alternatives of the default block nodes at root level in the last normalization step. All branches that represent a particular linear equation system are located at the root of the graph, which facilitates the following derivation. We present the construction of the equations from the graph for the first linear equation system. For each attribute defined in the production rule, we traverse the branch of the graph and count the occurrences of the corresponding attribute nodes. The first branch contains exactly one occurrence of the attribute node winner, so the winner size is 1. The same holds for the name. For the attribute player, there are multiple occurrences of the corresponding player's attribute node. In the outer branch, there are 2 occurrences, as well as in the first branch, of the star block node. Therefore, we first count the two occurrences in the outer branch and add these with the two occurrences in the star block node. However, since these two occurrences are part of an iteration, we multiply the number with the parameter x1. This parameter represents the number of iterations of the corresponding branch for this block. The resulting equation for the player size is 2 plus 2 times x1. Finally, we do the same for the referee size. The only occurrence of a referee's attribute node is in the second branch of the star block node. So the referee size completely depends on the parameter x2. With this concept, we can derive all equations for the corresponding linear equation systems, which are then embedded in the validate method of the corresponding class. For the validate method, the actual instantiations for winner, name, player, and referees are provided, such that the method tries to solve the linear equation systems with respect to these values. If there is an integer solution for one of these linear equation systems, then the corresponding model is valid. Otherwise, it is rejected by the method. Finally, we serialize the modified EMF-conform abstract syntax classes into the corresponding Ecore metamodel. The screenshot contains a visualization for the metamodel of our tennis tournament language. For the non-terminals, tournament, player, and referee, we generated the corresponding abstract syntax classes. The non-terminal reference winner was resolved into the explicit association winner-player. The original referencing string attribute is now derived. Additionally, each of the abstract syntax classes contains a validate method which operates on the number of attribute instantiations and validate the model instances. This concludes our approach of bridging MontiCore grammars to Ecore metamodels. In our concept, we translate grammar intricacies concerning non-terminal instances and structural features such as blocks. In the future, we can investigate the translation of semantically relevant terminals as well, since these terminals have an impact on the abstract syntax. To complete the bridge from MontiCore to EMF, we can also think of translating MontiCore's context conditions as additional well-formedness rules in EMF. In our approach, we serialize the generated abstract syntax classes into a corresponding metamodel. Since MontiCore supports including handwritten artifacts, future work could involve their serialization as well. We also investigated another concept of validating model instances in EMF. Our approach involves deriving linear equation systems that capture the grammar intricacies. Instead, we can also include automata that evaluate the model instances with respect to their underlying production rules. We decided to use linear equation systems to avoid the exponential blow-up when deriving deterministic finite automata. To complete bridging MontiCore and EMF, we can also investigate the backward translation from EMF metamodels towards MontiCore grammars. For example, we can think of generating standardized grammars for the abstract syntax representation of the corresponding metamodel. Furthermore, we enrich the derived grammar via inheritance with syntactic sugar. The goal of this thesis was the translation of MontiCore grammars into corresponding Ecore metamodels. We used the MontiCore feature of generating EMF-compatible abstract syntax classes. We enriched these classes and serialized them into corresponding metamodels. Additionally, we ensured model validity in EMF by also realizing the syntax validation of the generated parser on model instances in EMF. Our approach is completely integrated into the MontiCore infrastructure. Therefore, when generating EMF-conform abstract syntax classes, the language developer can configure MontiCore to retrieve the corresponding metamodel as well. Finally, by generating the Ecore metamodels, our approach enables EMF's wide range of tooling possibilities for arbitrary MontiCore DSLs. We conclude this presentation with a live demonstration of the metamodel generation for the tennis tournament grammar. This is an Eclipse instance with the required project for generating metamodels. First, we provide an overview of the modified MontiCore infrastructure. The first project we investigate is the MontiCore generator. The generator generates the EMF-conform abstract syntax classes. We extended this generator to integrate the grammar intricacies and MontiCore's parser validation functionality as well in the metamodel. Additionally, we added the new MontiCore plugin to the MontiCore Ecore metamodel generator. This generator takes the EMF-conform abstract syntax classes and serializes these into a corresponding metamodel. This plugin can also be configured to generate an Ecore modeling project for the derived metamodel, which serves as foundation for further language development in EMF. Finally, we have the language development project Tennis Tournament. In this project, we developed the Tennis Tournament DSL. Under source main grammars, we define the corresponding grammar. Here we describe the tennis tournament language with its players, referees, and optional winner. The project also features the POM XML to configure the project build and invoke the MontiCore toolchain. In line 92, we configure the MontiCore generator to generate EMF-conform abstract syntax classes. Additionally, we add a new plugin, the MontiCore Ecore metamodel generator. This generator serializes the corresponding EMF-conform abstract syntax classes, and we also define the tennis tournament grammar as additional parameter to derive a corresponding Ecore modeling project. So let's call the MontiCore toolchain and generate a metamodel for the given grammar. We right-click on our tennis tournament language development project and select Run as Maven Build. MontiCore now executes the code generation process for the grammar and creates the corresponding abstract syntax classes and also generates the metamodel. After the build process is finished, the metamodel should be located under Target, Generated Test Sources, EMF, Models, and the name of the corresponding grammar, so in this case Tennis Tournament. And here we see our corresponding Tennis Tournament Ecore metamodel. Since we configured the metamodel generator to create a corresponding Ecore modeling project for the DSL, we can import this project and further investigate the result of the Tennis Tournament metamodel. The modeling project is located in the same workspace directory as the original language development project. As a naming convention for the modeling project, we use the name of the DSL with the .model suffix. When the Tennis Tournament modeling project is imported, we switch into the Model Explorer to have a further look into the generated metamodel. Here we get this class diagram visualization of the language. After rearranging the elements, we see the abstract syntax classes tournament, player, and referee with their validate methods and the association winner-player for the resolved non-terminal reference. Based on this metamodel, a language developer can now enable additional tooling for the DSL.